In this video, we're going to use intermolecular interactions to understand trends in melting points and boiling points. When considering a solid, note that melting points increase as intermolecular interactions of the solid increase. Also, when we're thinking about liquids, boiling points increase as intermolecular interactions of the liquid increase. So as the number and strength of intermolecular interactions increase, both the boiling point and the melting point of a particular substance will increase. To understand that, let's look at these pictures shown here. In a solid, you can see that there's a lot of intermolecular interactions. Everything's packed together tightly in its crystalline form, and there's quite a bit of interaction. The more intermolecular interactions that you have, the more challenging it is going to be for that molecule to melt. In the liquid form, you have less intermolecular interaction, but still they play an important role. And when you have lots of intermolecular interactions, you're going to increase that boiling point. Once you've formed your gas, there's essentially no intermolecular interactions, so they really don't matter in this phase. Let's look at some boiling point examples. Note that what we are going to consider is the number of intermolecular interactions and the strength. In this particular example, the strength is what's important. We have here a hydrogen bond. You can see the donor here and the acceptor here. And we're going to compare this hydrogen bond in ethanol to the hydrogen bond in ethanamine, which has the same number of carbons. We're just swapping out a nitrogen for an oxygen. Again, here's the hydrogen bond donor, and here's the acceptor. So these molecules are very similar, with the only difference being an oxygen versus a nitrogen. Oxygen is in fact more electronegative than nitrogen, so the hydrogen bond, in this case on the top, is stronger. You can see the effect that the strength of this hydrogen bond has on the boiling point, because ethanol has a boiling point of 78 degrees, whereas ethanamine has a boiling point of only 17 degrees. So the strength of the intermolecular interactions played a key role in affecting the boiling point. Here are some melting point examples. Benzene over here has a melting point of 5.5 degrees. However, when you add more carbons to it, you see a huge increase in melting point all the way up to 80.3 degrees. What's happening here? Naphthalene has substantially more carbons than hydrogens, which is going to significantly increase the number of induced dipole interactions. So even though induced dipole interactions are considered to be weak, you can see that increasing those interactions is going to significantly affect the melting point. Anthracene, which has even more carbons than hydrogens and hence more induced dipole interactions, has a melting point of 215.8 degrees Celsius. So again, what we're seeing is increasing the number of induced dipole interactions is having a significant effect on melting point. In these examples here, first we're looking at ethanol, which can have one hydrogen bond, as opposed to methanoic acid, which can have two hydrogen bonds. The carbonyl oxygen can be a hydrogen bond acceptor, and down here you can have a hydrogen bond donor. So methanoic acid could potentially have two hydrogen bonds instead of just one. This significantly affects the melting point, which is now at 8 degrees, versus ethanol, which has a melting point of negative 114. Now we're just making a simple change from an H to a sodium, and now suddenly we've gone from hydrogen bonding to an ion-ion interaction. That ion-ion interaction is incredibly strong, way more strong than hydrogen bonding, and now you have a melting point of 253 degrees Celsius. Hopefully I've been able to demonstrate that both the number of intermolecular interactions and the strength of them are important for predicting trends in melting points and boiling points.